Shrinking and expanding gaps. Some motion-based word problems involve two travelers moving toward or away from each other. And sometimes some basic rules can simplify these otherwise very difficult problems. Before I can talk about these basic rules, we have to discuss some terminology. These are four basic cases I'm going to discuss here. And in particular, I want to talk about cases 1 and 2. In colloquial language, we'd say that in case 1, that we have two cars moving head-on. Sometimes they're moving in this, we'd say moving in the same direction. Case 2, we'd say moving in opposite directions. And I'm going to say that a lot of the colloquial language we have around this is actually a bit distorting, and it makes it hard to understand what's going on mathematically. So I'm going to lump both these cases together and say both of them are cars heading in opposite directions. And what do I mean by that? Well, the green car is heading west. The purple car is heading east. And so in either case, east is the opposite of west. They're moving in opposite directions. In other words, if you point an arrow in the direction of where they're going, those arrows point in opposite directions. And it doesn't matter whether they're getting closer to each other or getting further away from each other. Also notice that it makes sense to talk about these using the same language because they're really part of the same story. If the two cars are heading toward each other, what's going to happen is they're going to pass each other and then keep on moving in opposite directions. So case 1 and case 2 are actually part of the same story. Much in the same way, case 3 and case 4, I'll call those moving in the same direction. Case 3 and case 4 are also part of the same story. Because if the faster car is behind the slower car, it's going to close the gap, it's going to catch up past the slower car, and then later on, it's going to be pulling away and getting further away from the slower car, leaving it behind. Mathematically, cases 1 and 2 belong together, so I will call those opposite directions. The other two I'll call in the same direction. So that's how we're going to talk about these cases. First of all, we'll talk about the two travelers in opposite directions. When two travelers are in opposite directions, we always add the speeds. And this is true whether they're approaching each other, then the sum of the speeds is the speed at which the gap is shrinking. If they're moving away from each other, then the sum of the speeds is the speed at which the gap is expanding. But in either case, we add if they're moving in opposite directions. If they're moving in the same direction, we subtract the speeds, bigger minus smaller. So if the faster traveler is in front, then the difference in speeds is the speed at which the gap is expanding. If the slower traveler is in front, the difference in speeds is the speed at which the gap is shrinking. And again, notice they're part of the same story, that if it starts out with the faster car behind, then later on the faster car is going to be ahead. And in both cases, we're subtracting the speeds. So let's just think through a few scenarios here to make sure we understand this. Scenario number 1, car 1 is going 50 miles an hour south, car 2 is going 70 miles an hour north, and they are approaching. So the velocities are pointing in opposite directions, one pointing south, one's pointing north. So we add the speeds, 50 plus 70 is 120, and they are approaching, so the gap between them is getting smaller, so the gap is shrinking at 120 miles an hour. Scenario number 2, car 1 is going 50 miles an hour south, and car 2 is going 70 miles an hour north, same as before, but now they are moving apart from each other. So now the gap is expanding. We still add the velocity because they're still moving in opposite directions, but now the gap is growing at 120 miles an hour. And notice again, scenario 1 and scenario number 2 could be part of the same story. If we could start in scenario 1, the cars would be getting closer and closer. They would pass each other in opposite lanes, and then later on, they'd be moving further and further apart from each other. Scenario number 3, car 1 and car 2 are both going west. Car 1 at 50 miles an hour, car 2 at 70 miles an hour, and the slower car, car 1, is ahead. So because the slower car is ahead, the faster car is behind, the gap is shrinking, and the The speed at which it's shrinking is the difference in the velocity. 70 minus 50 is 20. The gap is shrinking at 20 miles an hour. Scenario number 4, car 1 and car 2 are both going west. Car 1 at 50 miles an hour, car 2 at 70 miles an hour. But now the slow car is behind. Well, now we still subtract, but now the gap is getting bigger because the faster car is in front and it's leaving the slower car behind. So the gap is growing at 20 miles an hour. In a problem in which the gap is obviously shrinking or expanding, we could set up a d equals rt for each traveler, but sometimes it saves time to set up a d equals rt equation for the gap itself. If we figure out the speed at which the gap is shrinking or expanding, we can relate the two individual speeds by simple addition or subtraction. And this is a big strategy for this kind of problem. Here's a practice problem. Pause the video and then we'll talk about this. A car and truck are moving in the same direction on the highway. The truck is moving at 50 miles an hour and the car is traveling at a constant speed. At 3 p.m., the car is 30 miles behind the truck, and at 4:30, the car overtakes and passes the truck. What is the speed of the car? Well, first of all, we'll focus on the gap. And the gap, we know that in a time from 3 to 4:30, so that's an hour and a half or 1.5 hours, the gap shrunk from 30 miles down to 0. And we'd like to know the speed. And so that is 30 divided by the time of 1.5, or 30 divided by 3 over 2. We can rewrite that as 30 times 2/3. Cancel the 3's, we get 10 times 2, which is 20. So the gap speed is 20. In other words, the gap was getting smaller at a speed of 20 miles an hour. Well, that must be the difference in the speeds. And so if the truck is moving at 50 miles an hour, the car must be moving 20 miles an hour faster than the truck. So that must be 70 miles an hour. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so City J is 480 miles north of City K. At 10 a.m., car M starts driving south, and car N starts driving north, and it's going twice as fast as M. Both cars maintain constant speeds, and they pass each other at 2 p.m. going in opposite directions. What is the speed of car N? So notice that it's going to make a lot of sense to focus on the gap. The gap goes from 480 miles to 0 in 4 hours. So at 10 a.m., those two cars are 480 miles apart. 4 hours later, they are 0 apart. They're passing each other going in opposite directions. So the gap goes from 480 miles to 0. So we can figure out a gap speed. The speed of the gap would be 480 divided by 4 is 120. So the gap is shrinking at 120 miles an hour. Now, because the cars are moving in the opposite direction, we know that we add the speeds. So the speed of M plus the speed of N equals 120. But we know that N is twice as fast as M, so we can plug that in. R sub M times 2 times R sub M equals 3 times R sub M. That equals 120. Divided by 3, we get the speed of car M is 40, and our N is going double of that. So our N is going 80 miles an hour. So we go back to the answer choices and choose 80. Here's a tricky problem. Pause the video and then we'll talk about this. Cars P and Q are approaching each other on the same highway. Car P is moving at 49 miles an hour and car Q is moving at 61 miles an hour. So they're going in opposite directions. At 2 p.m., they're approaching each other and are 121 miles apart. Eventually they pass each other. At what clock time are they moving away from each other and are 44 miles apart? So this looks like a really, really hard problem. But notice that the whole thing is in the same case of cars moving in opposite directions. And this is why it's mathematically advantageous to talk about those two cases together, whether they're moving toward each other or away from each other. They're moving in opposite directions. So the gap is shrinking at the sum of their velocities. 49 plus 61 is 110 miles an hour. So that's the speed at which the gap is shrinking. So it's shrinking at that speed when they're moving toward each other. And then it's expanding at that speed once they pass each other. But really, we can add both those distances, but in both cases, it's the same gap speed. In one case, it's getting smaller, one case it's getting bigger, but it's the same speed. So we can just add those distances up. 121 plus 44 equals 165. And then for time is just distance divided by speed. So 165 divided by 110, both of those numbers are divisible by 11. So when we divide by 11, we get 15 over 10, or 1.5 hours. And so 1.5 hours later is when they're 44 miles away from each other. 1.5 hours after 2 p.m. would be 3:30 p.m. So we go back to the answers and choose answer choice B. Going in opposite directions, we add the velocities. Going in the same directions, we subtract the velocities. Think about the directions to determine shrinking and expanding, and solving a d equals rt for the gap can enormously simplify such problems.